last time we looked at how the limit as h approached 0 of the difference quotient gave us what we call the derivative, the slope of the tangent line to a function at any given x value. So today we're going to use that limit to prove some rules, or really just one rule today, that's going to be exceedingly helpful so that you don't have to do all of that expansive limit stuff on every single derivative that we need to find, because that's what the whole first half of this class is really about, is derivatives. So the first one that we're going to prove, we're going to do two little rules. First is this one, that the derivative of a constant is 0. And we're going to prove this by doing, well, a limit as h approaches 0 of our function at the x value of x plus h. So if we think about what's f of x plus h mean, it just means what's the y value of the function, or what is the function at x plus h? Well, if our function is just a constant, y equals c, it doesn't really matter what our x value is, right? The constant remains the same. So f of x plus h is c, and f of x is also c, as we put this into that limit we talked about last time. The limit as h approaches 0 of f of x plus h minus f of x all over h. So we've got the limit as h approaches 0 of c minus c over h. And obviously we can simplify the numerator of that to give us a limit as h approaches 0 of 0 over h. And we can't just plug 0 into this, because then it becomes 0 over 0, it becomes indeterminate, right? But we can simplify. We know that 0 divided by h is always 0. So now this is just a limit as h approaches 0 of 0. Well, as we're approaching 0, 0 is 0, right? In fact, 0 is always 0. So no matter what the constant is, the derivative of that constant is 0. And hopefully this makes sense, right? Because if the function is just a constant, here's my x and my y-axis here. Here's some function, let's say y equals c, right? The derivative talks to us about the slope of the tangent line. Well, the slope of the function at any given point. What's the slope of this function at any given point? Well, the slope of the horizontal line is always 0. Therefore, the derivative of a constant is always going to be 0. The next rule we're going to look at, which is an exceptionally helpful rule, is called the power rule. So we're going to look for the derivative, and this is the notation we're looking at, d dx, right? The derivative with respect to x of x to the n. So basically, a variable to some power n, some number, x squared or x to the fifth or something like that. And we're going to do a quick little proof. It doesn't look like it's going to be quick with everything that we've got written out there already, but it's going to be a real quick little proof that proves this is true for all natural numbers, right? When n is any natural number. And later on during this unit, we're going to prove that this rule that we're going to develop actually works for all real numbers. And we're going to apply it to all real numbers today. But this little proof is really only going to be for natural numbers. So if we were to write out the derivative with respect to x of x to the n as a limit, we get the limit as h approaches 0 of the function at x plus h, so x plus h to the power of n, minus x to the n all over h. And looking at this, x plus h is like the form a plus b to a power, a plus b to the n. So we can just use the binomial theorem and Pascal's triangle to expand out x plus h to the n. So everything from here to here, that is just the expansion using the binomial theorem of x plus h to the power of n. So we've got that minus the x to the n, and then all over h. So it's our limit as h approaches 0 of x plus h to the n minus x to the n over h. And just like with all those other limits that we did, we can see that the x to the n and the minus x to the n are going to cancel out, right? All the terms that didn't have an h in them should cancel. And now everything that's left has an h in it. This one's got an h squared, an h to the third. They've all got h's in them all the way down the line. So we should be able then to just divide term by term everything that's left after getting rid of those x to the n's by h, right? So if I divide n x to the n minus 1 by h, that should just give me n, let me try to write my limit here. Limit as h approaches 0 of n x to the n minus 1. And then this next one should be n minus 1 over 2 factorial x to the n minus 2 times h now, because h squared divided by h should just be h. And so on down the line. I'm going to skip this one here, but it's going to have all of this stuff except with an h squared. And then this second to last one here should now be n x h to the, well, if I drop down by 1 power there, if I divide n h to the n minus 1 by h, that should be h to the n minus 2. And then that last one should be h to the n minus 1. And now, as h goes towards 0, this term right here, which has an h in it, this becomes a bunch of values here times 0. It cancels out, becomes 0. And every other term in there that has an h in it, like all of these, come out to be 0. And this one, which has an h in it, comes out to be 0. And this one, which has an h in it, comes out to be 0. And so all that we're left with here is just n times x to the n minus 1. And this is what we call the power rule. The derivative of x to the power of n is n times x to the n minus 1. So effectively, all we do is we take the power, bring it out in front as a coefficient, and then we drop the power by 1 to make it n minus 1. And this rule is going to be exceedingly important during this unit and literally everything we do for the entire rest of the school year. So we're going to practice some straightforward little derivatives using the power rule today. We'll add a couple little tiny pieces to it, and then we'll be done for the day. So there's the rule. The derivative with respect to x of x to the n is equal to n x to the n minus 1. And our first notation that we need to be aware of is f prime of x. That means the derivative of f of x. So if I'm looking for the derivative of f of x, and f of x is x to the 7th, I'll just use the power rule. I'll bring that power out to the front, and I'll have 7x to the 7 minus 1, or just 7x to the 6. And you don't need to write the 7 minus 1. You should be able to just look at x to the 7th and say, oh, its derivative is 7x to the 6. And that's certainly a lot better than writing it out as a limit as h approaches 0 of x plus h to the 7th power minus x to the 7th all over h, and then having to expand out x plus h to the 7th. That's just a mess. It's much easier to use the power. So here, if y is x to the 4th, y prime, or the derivative of y, should just be 4x to the 4 minus 1 power, 4x cubed. And over here, the derivative with respect to x of x to the 50th should just be 50x to the 49th, 50 minus 1. So one little piece that we're going to add in here now is what happens if our function is being multiplied by a constant. And what if I have a constant times u of x? So down here, something like 5, a constant, times x to the 4th. Well, if we think about this as a limit, right? The limit as h approaches 0 of, let's see, f of x plus h, or u of x plus h, should be c times u of x plus h minus c times u of x all over h. Well, what can we do with that? With the limit, if we factor out a c from everything in the numerator, constant, we can pull the constant outside the limit. So we have c times the limit as h approaches 0 of u of x plus h minus u of x all over h. Well, what is u of x plus h minus u of x all over h? As h goes towards 0, it's the derivative of u. So we can just multiply that constant by the derivative of u. And we don't actually have to do any extra work there. So what that means is if I have the derivative with respect to x of 5x to the fourth, that's the same as 5 times the derivative with respect to x of x to the fourth. So that would be 5 times 4x cubed, which would just be 20x cubed. And again, you don't need to write all these steps. You should just be able to look at this and say, oh, I need to multiply that power by that coefficient. That gives me the 20. And then I drop my power by 1. For this next one, this notation, capital D with the subscript x, just means the derivative with respect to x of 11x to the 8th. So we'll do the same thing. We'll multiply the 8 by the 11 to get 88. And then we'll drop the power by 1. This also works, and we're not going to write out a proof of this one, if we have multiple different functions being multiplied together. So if I'm looking for the derivative of f of x equals x to the 5th plus 3x cubed, I can just take each derivative separately and then add them together. Okay? Because if I had a limit of one function plus another function, I could take each limit separately and combine them together. So the same works with derivatives. So the derivative of x to the 5th should just be 5x to the 4th. And then the derivative of 3x cubed ought to just be 9x squared. And there's our derivative. Same thing should work here. 4x to the 10 should become 40, the 4 times the 10, x to the 9th. The 1/2 x to the 6th, as we multiply 1/2 by 6, we get 3. That should be plus 3x to the 5th. The 5x to the 5th should become 25x to the 4th. The minus 2x, if we think about that one, that's like minus 2x to the first power. And so if I take the derivative of that, that should be negative 2x to the power of 0. Well, x to the power of 0 is just negative 2. So the negative 2x becomes minus 2. And then the plus 3, our first rule of the day was the derivative of a constant is 0. So that one just falls off. And this is our final answer. So we're going to spend a bit of time now just practicing a few more of these. We're going to use the power rule here on these few. Even though these are not natural numbers, the power rule is still going to work. And again, once we learn how to do some derivatives with logarithms and such, we're going to prove that it works for all real numbers, but not for today. But we'll still use the rule in practice. So the derivative with respect to x of x to the negative 1, same thing applies if you're using the power rule. We'll do negative 1x to the power of negative 2. We'll still drop down from negative 1 to negative 2. You can write your answer like this, or if you prefer, you could write it as negative 1 over x squared. Either one is acceptable. You got to know that you can convert back and forth between the two, but I'm fine with either answer. And they would be fine with that on the AP test either way. Here we're going to get negative 4x to the, when we drop by 1, negative 5. Or negative 4 over x to the 5th. Either one is good. And just be careful. A lot of people make the mistake of making that negative 4x to the negative 3, forgetting that dropping by 1 from negative 4 takes you to negative 5, not negative 3. This will work with fractional powers, like x to the 3/2. This derivative should become 3/2 out in front. X to the, well, 3/2 minus 1 is just 1/2. So 3/2 x to the 1/2. You could write it as 3 root x over 2 if you want. Any of that would be just fine. And even if we don't have it written as a fractional exponent, we should be able to take something like the square root of x and say that's x to the 1/2. So if we take the derivative of that, we should end up with 1/2 x to the 1/2 minus 1, or negative 1/2. And this is normally written as 1 over 2 root x. This answer here is also perfectly acceptable. But this is another one that's going to be helpful because it shows up all the time with the square root of x. If you just have that one memorized, the derivative of root x is 1 over 2 root x. Well, we'll find a couple more derivatives here. F prime of x for this first one. X to the 2/3 should become 2/3 x, and then we will drop 2/3 by 1. So that'll give us negative 1/3. And then for the plus 4x to the negative 3, we should get minus 12x to the negative 3 minus 1 to the negative 4. And down here, f prime of x should be 1/5 times 5 is just 1. So we now have x to the 1/5 minus 1, which would be negative 4/5. And the minus 2, x to the negative 5, should become a positive 10x to the negative 5 minus 1, which is negative 6. And our last one, 3/2 times 4 is 12/2, or just 6. So we have plus 6x to the 4 minus 1, 6x cubed. Do 2 more of these before we talk about what's called higher order derivatives. So we're looking for the derivative of this. First, we should probably convert all of these into fractional exponents. That's x to the 1/2 plus 5x to the 3rd power means a 3 in the numerator, and a 4th root means a 4 in the denominator of that. And then a 10th root of x would be x to the 1/10. So if we're looking for the derivative of that, we've got 1/2 x to the negative 1/2, or 1 over 2 root x if we're just memorizing that rule. 5 times 3/4 ought to be 15/4 x, and then 3/4 minus 1 is negative 1/4. And then minus 1/10 x, the 1/10 minus 1 would be negative 9/10. And down here, 1 over root x is the same as x to the negative 1/2. So when we take the derivative of x to the negative 1/2, we should get negative 1/2 x to the negative 1/2 minus 1, or negative 3/2. And then 5x cubed should just be 15x to the 2nd power. That's not all there is to the power rule. What we do need to know is that sometimes we'll be asked to apply the power rule multiple times to find what we call higher derivatives, or higher order derivatives. And these are the notations that you should know, 4 different notation types for the derivative. So if my function is f of x, the derivative is f prime. The second derivative, which will be very useful to us throughout this year, is f double prime. A third derivative would just be triple prime, and then after that, you just put a little 4 in the superscript, or a 5, or an n up there, indicate higher derivatives. Same if we just talk about y prime, y double prime, second derivative, and so on. And then down here, sometimes we call it dy dx. Right? Well, the second derivative of y with respect to x is written as this, right? With the superscript 2 on the d in the numerator and on the x in the denominator, meaning that we are taking 2 derivatives and we've taken it with respect to x both times. Right? And then down here, a third derivative of y with respect to x all 3 times, and so on. And same here, being the exact same thing. These are just the notations in this lesser used style of the derivative. So let's see if we can find the first 4 derivatives of f of x equals 2x to the 5th. So we've got f prime of x using the power rule ought to be 10x to the fourth, or 5 minus 1. The second derivative ought to be 40x to the third, 10 times 4, and then drop 4 by 1. Our third derivative ought to be 120, 40 times 3, x to the second. And our fourth derivative ought to be 240, 120 times 2, and then x to the first. If we're looking for the first 4 derivatives of 4x to the 3 halves, we should get f prime. The first derivative is 4 times 3 halves, or 12 halves is 6. So 6x to the 1 half. Our second derivative will just be another application of the product, or the power rule. 6 times a half is 3. So 3x to the negative 1 half. Our third derivative should just be negative 3 halves x to the negative 3 halves, right? 3 times negative a half would be negative 3 halves. And if we drop negative a half by 1, that's negative 3 halves. And our fourth derivative with respect to x here should be 9/4, the negative 3 halves as the coefficient times the negative 3 halves in the power. 9/4 x to the negative 5 halves. And here we are going to find the first 4 derivatives of 3x to the negative 2. So our first derivative ought to be 3 times negative 2, or negative 6, x to the negative 3rd power. F double prime of x ought to be 18x to the negative 4 power. Our third derivative ought to be 18 times negative 4, ought to be negative 72. So negative 72x to the negative 5 power. And our fourth derivative here ought to be negative 72 times negative 5, which would be 360x to the negative 6. And we'll do one more here. We've got f prime of x is equal to 50 times the 2, ought to be 100. And then x to the first power, or just x. Our second derivative here, now this is 100x to the first power, so we'll multiply by 1, which is just going to give us 100. And then if we drop that by a power, x to the first, x to the 0, x to the 0 is just 1. And so this is really just 100. And then our third derivative here is the derivative of a constant. And the derivative of any constant is just 0. And then our fourth derivative is the derivative of 0, which is, again, just the derivative of a constant, or just 0. And that's the whole idea of applying the power rule to find derivatives. So next time, we're going to take a look at what happens when, instead of just having a bunch of functions added or subtracted from each other, or a singular power rule function, what happens when we have 2 different functions that are being multiplied by each other and take those derivatives. So that's it for today.